I'd like to quickly say that I'm really, really excited to have Anthony here. I'm going to introduce him in a second, but just if you haven't taken a look at the company Anthony's from, I encourage you to get online and take a look at, I'm going to pronounce it wrong, Anthony, is it Kaggle or Kaggle? Kaggle, okay. It's a fascinating company that actually holds data science competitions. So companies will post a large amount of money in a big data set and say to a group of data scientists, help us figure out, you know, the answer to a question we've got, and groups of teams will compete for this. So in addition to a data science platform, it's also a new way of recruiting, because Anthony basically has a leaderboard of the top data scientists in the world that are competing in these competitions. And it's a fascinating way that I think some of the recruiting is changing, and in fact there's going to be a real shortage of the skill sets needed in data science. I don't have kids, but if you have kids, they should be taking statistics, because, you know, it's really, really important. I think we all probably need to get more experience and remember what we learned in our basic statistics classes. So to formally introduce Anthony, Forbes magazine named him as one of 30 under 30 a couple of years ago, and the MIT Tech Review also named him on one of the 35 innovators under 35. He's from the University of Melbourne and was awarded an Alumni of Distinction Award, holds a first call honors degree in econometrics from the University of Melbourne, and is published in The Economist and Harvard Business Review. My understanding, though, is that actually the main reason that Anthony has come to Houston to work in oil and gas is that he's a big fan of barbecue. And he was looking for an industry, and somebody on the panel told me Anthony really likes barbecue. So we're glad you're here, and I'm going to turn it over to him to give us a little bit of background on the program tonight.
So in Australia, where I'm from originally, the company is always pronounced Kaggle, which is much less awkward than the American pronunciation Kegel, which sounds a bit like pelvic floor exercises. So I've come to regret the company name since moving across to the US. So Dan Ariely, who's actually an MIT, was an MIT professor until recently, said recently that big data is a lot, he has this crude analogy, that big data is a lot like teenage sex. Everybody talks about it, nobody knows how to do it. So nobody knows how to do it. Everybody thinks everybody else is doing it, and therefore everybody says they're doing it. Part of the, there's a lot of vague, nebulous descriptions of this thing called big data. And my aim tonight is to try and put, before we lead into a panel discussion, to try and put a little bit of meat on the bone and give you at least our perspective or my perspective on what's unique. As Roberta said, a lot of what's happening now is real, but what about it is, in my opinion, what about it is real and what about it is not. I think there are three things that have changed really over the last 5 or 10 years. So thanks to companies like Yahoo, Google, Facebook, we're now able to store and query much more data than we've ever been able to store and query historically. The second thing that is real is that we're collecting, we've got, sensors are ubiquitous now, we're collecting much more data, we're able to collect much more data than we've ever been able to collect before. We all have smartphones in our pockets that are full of sensors. A lot of us have things like Nest thermostats that are now connected to the internet that collect a lot of information about us. The third thing that is real that doesn't get a lot of discussion, which is where I'm going to focus my attention tonight, is on our ability to do more with the data that we collect. So there have been pretty remarkable developments in a field, it goes by lots of names, data science. I'm going to use machine learning tonight. I'm going to talk about some of the advances in machine learning and some of the things that are now possible that weren't possible 5 or 10 years ago. Out of interest, show of hands who's heard of machine learning before and feels like they have a bit of a handle on it. All right, to open up, I'm going to start with, I'll open up with, so I was going to cover three three basic. I was going to stage this talk in three, go through three different topics. First, I was going to give a bit of an introduction to machine learning, just for those who aren't familiar with it or would like a little bit more of a specific definition. I was going to open up by giving a bit of a description of machine learning. The second thing I was going to do is talk about some of the things that machine learning is able to do today that it wasn't able to do, as I said, 5 or 10 years ago. And then I'm going to end by hopefully teeing up the panel discussion nicely by talking about where we think some of the interesting things, some of the potential is within the oil and gas industry. So machine learning is basically the ability to take a data set and find patterns in that data set that will help you make predictions or understand that data set better. The example I often give when I'm describing machine learning comes from the first use case that I'm aware of. So the guy on the screen, his name is Arthur Samuels, and he wanted to build a machine that he could play checkers against. And so his first approach to this was to start by basically taking the way he would approach a checkers game. So if he, in this board configuration, he would make this move, in this board configuration, he would make this move, and coding up the machine basically with these rules or these if-then-else statements. Now, the problem with taking that approach is, first of all, it's very laborious. There are lots of potential configurations of a checkers board. The other thing is that he was never going to be able, in taking that approach, to build a machine that could play checkers better than he could. And so, in order to build a real checkers playing machine that he could play against competitively, he had to take another approach. And the approach he took was to code up a machine that could, the more games of checkers that it played, the better able to learn from the patterns of games that turned out to be successful and the patterns of games that turned out to be unsuccessful. So the machine could start to correlate certain board configurations with victory and other board configurations with I guess, a defeat. And over time, the checkers machine would get better and better and better the more games of checkers that it played. Now, not only did this checkers machine eventually manage to beat Arthur Samuels, but it actually ended up managing to beat a checkers master, grandmaster. Now, this was a precursor to IBM's Deep Blue machine, and which was a precursor to the IBM machine that won Watson last year. Now, I think if you look at those IBM publicity stunts, actually, they're a really good way, not to be cynical, I actually think they're actually a really good way to track where the state of the art is in machine learning. So we started, machine learning could start off by winning a game of checkers, and then it was able to win a game of chess, which is against a grandmaster, which is a much more complex game. And if you think back to 2012, when IBM Watson built that machine that won Jeopardy against the Jeopardy champions, well, that was another order of complexity again. That machine, and being able to build a machine that can take text as an input and answer questions is pretty remarkable and pretty sophisticated. And in order to be able to do that, you've got to be able to deal with much, much messier data sets than had needed to be dealt with historically. And that's the crux of what's really changed over the last 5 or 10 years. We now have the technology that allows us to go from the ideal world that is a checkers board or a chess board to a much messier, more real-life situation, such as, a game of Jeopardy is not so real life, but it's a much more complex environment. Now, this chart that I'm showing now is produced by Tom Davenport, who's got a book called Competing on Analytics. And he talks about, he's got a hierarchy of, I guess, on the x-axis, degree of intelligence, and the y-axis, the amount of competitive advantage that a company gets for a given level of intelligence. And so at the lower levels, you've got the things that companies have been doing for 10 to 20 years, so things like standard reporting, OLAP cubes. As you move up to the top right, you have things like predictive modeling and optimization, and those are the things that those are the two I guess, elements of data-driven decision-making that machine learning really enables. So the predictive modeling is what is going to happen next. And the optimization is, given my expectation of what's going to happen next, how do I react to it? Or what is my best move? So we're going to move on to the second part of the talk, which is around some of the things that are now possible, given what we can now do with machine learning. There's a great book by Andrew McAfee and Eric Brynjolfsson, who actually also are at the MIT Sloan School, called Race Against the Machine. They've actually got a new book out now called The Second Machine Age. But in their first book, they talk about they itemize a whole lot of things that computers can now do that we never thought they'd be able to do. The first case in point is driving a car. So this is the authors of that book, Andy and Eric, in front of the Google self-driving car. Now, the Google self-driving car is powered by machine learning algorithms. The way this works is it will predict what's going to happen as it drives an extra foot, an extra 10 meters, what's going to happen over the next 10 meters. And as a result of the prediction about what's going to happen, what is the optimal response that the car should make? Now, if you tried to program a car to drive on a road, it would be very difficult to do that with if-then-else statements. But the way the Google engineers have gone about it is they basically train the car by driving it as much as possible, and the more different road situations it sees, the more it's able to learn, and the better it is the closer it gets to being able to drive itself. The other example that Andy and Eric give in their book is human translation. So for many years, there have been linguists who have tried to translate one language to another using what might be called language rules or a language model. So the thing that they've consistently found is there are too many anomalies in language to use language models or language rules. Now, Google Translate, which was really the place that cracked this problem, Peter Norvig, who I'm not sure, I think he may be a Stanford alum, not an MIT alum. But what Peter Norvig did was he started off with a corpus of documents that were translated into many languages. So by way of an example, he started off with things like UN and EU communiques. So you have the same text that has been, by professional translators translated from one language to another. And then he would move on to books that have been translated into multiple languages, and basically trained a machine learning algorithm on these sources, these different versions of the same text. And the more text he was able to feed in, the better the translation engine got. And so for those of you who haven't used Google Translate, I strongly recommend trying it out. It's pretty remarkable. I find it's a very good way to impress overseas friends with your knowledge of their language. I referenced earlier Jeopardy, the IBM Watson Jeopardy winning machine. So it beat Jeopardy champions, as mentioned earlier. And what they did was they ingested a corpus of things like Wikipedia data and other knowledge corpuses, and trained the algorithm to ask questions in a response to an answer. Again, you could never do this using an if-then-else approach or a rules-based approach. There's just too many permutations. And so a machine learning approach works very well here. Same goes for e-discovery. So it used to be the case, my wife was a litigator. That was her first job, and she used to spend an enormous amount of time laboriously going through documents, trying to figure out which were relevant to a particular litigation and which ones weren't. Now you have e-discovery software that can be trained on a small portion of all the documents that are attached to a certain case, and can algorithmically pick out which are the relevant documents. Talk about a couple of examples that Cowgirls done, and this one in particular is one I'm particularly proud of. I'm proud of it because when we were approached about this problem, I thought it sounded like science fiction and not possible. But we built an algorithm in conjunction with the Hewlett Foundation and attached to the Department of Education around grading high school essays. So taking essays that were written by high school students, grades 7 to 10, I believe. Each of them had been graded by 2 teachers, and the idea was to train an algorithm that could match the average grade of the 2 teachers. Now, it turned out that the winning algorithm was about as reliable as the teachers in grading essays, which got us a lot of, somewhat not positive press. So the way we judge this is that the discrepancy between the algorithm and each teacher was about the same as the discrepancy with discrepancy between the two teachers. The other example from another science-driven industry, not oil and gas, is the pharmaceutical industry. So we've done a lot of work with the likes of companies like Pfizer and Merck and Genentech in an area called chemical informatics. So taking chemical compounds and predicting which of them are going to be toxic, which of them are going to bind to a certain target. And this is basically used in very early stage drug discovery in order to triage the most likely candidates for new drugs. And so what we do is, say Merck's tested 10,000 drugs in the lab over the last, say, 5 or 10 years, and they've got good data on whether those drugs were toxic, what levels of toxicity, what sort of off-target effects, what sort of on-target effects. We would train an algorithm on all the data all the drugs that they had tested in the lab in order to try and triage the millions of potential chemical compounds that they could possibly be testing in the lab next year. Now, just to tee up some of the discussion about oil and gas, our company does not have, we've worked with a whole lot of industries. So about a 3.5-year-old company, and we've worked with around about 20 Fortune 500. So everybody from some of the technology companies, which have been the early adopters of advanced machine learning, like Amazon, Microsoft, Facebook, through to the pharmaceutical companies that I referenced earlier. And we actually think, I'll give you a bit of a background on how some of the work we've done with some of these companies, just to give you a bit of a sense for how it all works. I think Roberta gave a bit of a sketch early on. And then use that as a lead-in to where the interesting aspects of big data are potentially for oil and gas. So we're most well known, it's a component of what we do, but we're most well known for these data mining competitions that we run. And the way I characterize these is these are basically a sport for the kids who weren't that good at soccer growing up. So what happens is somebody will come to our website and they'll be able to download a data set, and we have split that data set into 2 parts. So let's say, just to give you a toy example, you're a bank and you want to predict who's going to default on a loan. We'll take age and income and try and predict who's going to default. And we will score you. We have a second data set where we know the answers. We know who this is all historical data. We know who defaulted. And so what we're doing is we're trying to predict who defaulted based on a second data set. And so people will upload their algorithms. They'll make their predictions. And we'll score them in real time. This is why I call it a sport. And we'll show them exactly how they're performing relative to each other. Now, they can each make up to 1 entry per day, and it's amazing the effect of putting a leaderboard in front of people. So this is some work. One of our very early customers in the US was NASA's Jet Propulsion Lab in Pasadena, California, and this was an image analysis problem that we did with them. And now, to explain this chart, the y-axis is the error rate. The lower the better. The x-axis is time. So in this case, Martin O'Leary Martin O'Leary was a PhD student in glaciology from Cambridge University. It happened to be the case that in his glaciology research, he used a lot of image analysis algorithms. So what Martin did was he put in a first entry and he got to first place on the leaderboard, and he was very pleased with himself. That is, until somebody else passed him. And so what does Martin do next? Whereas he would have ordinarily stopped, Martin keeps working till he gets ahead of them. Somebody passes him, he gets ahead of them, and they keep passing each other until the point where, notice the increments by which they're passing each other get smaller and smaller and smaller. What these data scientists are doing is they're pushing each other until the point where they've basically sucked everything there is to get out of the data set. So in any data set, there's noise and there's signal, or there's richness. And you get to the point where you've really extracted everything out. Now, the interesting thing is no one's sharing their results with each other. What's happening is Martin shows what's possible, and then somebody else comes along and matches Martin or outdoes Martin, and then that shows Martin what's possible. And they're sort of catalyzing each other to do better than they ordinarily would. We call this effect internally the Roger Bannister effect, after the guy who broke the 4-minute mile. So for anyone who doesn't know the story, the 4-minute mile world record was 4 minutes and 1 second for about 10 years. And in 1954, Roger Bannister broke it, and then 46 days later, John Landy broke it, and before long, everybody was running a mile in less than 4 minutes. You see a similar effect here. Now, we, as mentioned, we now have a community of 150,000 statisticians and data scientists who've competed in these competitions. And we actually have them ranked from 1 to 150,000 based on their performances. So this is, I think this is the current top 10, or at least the top 10 when I took this screenshot. Now, we've been through, as mentioned, we've run about 360 competitions, and competitions are a component of what we do. And of all the industries that we've worked with, we actually think that there's more potential for big data and machine learning in oil and gas than any other industry. And to give you a sense for where we think the opportunities are, and then again to tee up the panel discussion, I was going to go through a couple of use cases. First of all, to distinguish the big data approach from a traditional approach, the way one typically would approach an oil and gas problem with a machine learning focus is you'll start off with all the data that's available on a given problem. And then you'll train the algorithms. The algorithms will pick out the bits of data that are giving you signal and predicting something like, you know, the likely productivity of a different area. And then the machine learning models will basically figure out what are the interactions between these features. So not just what are the variables that are important and how important are they, but how do they interact with each other. And a machine learning algorithm can go through and train on many, many different permutations of the data and the interactions between the different data sets. So whereas a typical a geologist can take into account a certain number of heuristics that they can hold in their head, a machine learning algorithm can handle a lot more complexity. So it can handle a lot more features. It can handle non-linearities in those features, as well as interaction between those features. So I was going to show you two areas where we think there's particular potential for big data within oil and gas. The first is around evaluating acreage. So this is to make decisions like where to drill, how much to bid on a lease, how much capital should I be allocating to the different leases or the different areas that I hold. And so what this looks like is you can select a bit of acreage, ingest all the data that you have, so a combination of geological data from core wells and well logs, as well as some of the nearby production data, and train an algorithm that will help you predict what the productivity of that acreage is. Now, over time, more wells are drilled, so both inside your acreage and outside your acreage. So you decide you want to purchase that acreage or acquire that acreage. You drill some wells inside the acreage and some wells outside the acreage. This helps with making a capital allocation decision. You now have a repeatable approach to measuring where the best potential is of all the acreage that you hold, and so you can decide, if you have acreage in the Permian Basin and acreage in the Marcellus, how much capital should be allocated, for instance, to each of those business units. The other area that we see as being big potential within oil and gas is around optimizing recovery, so specifically optimizing field development plans and completion strategies. And so what this looks like is being able to take all your very detailed completion data, so things like the length of the horizontal, the longitude and latitude to where you're going to place your next well, the length of the horizontal, the amount of proppant, the number of frac stages, and based on the completion parameters that you're planning to complete your next well with, make a prediction around not just what the ultimate recovery from that well will be, but also first 12 months production and the decline curves with the uncertainties around those predictions. And so what this allows a completion engineer to do is to manipulate the parameters, the completion parameters, and get to a point where you are really, given the cost of the different treatments, you're optimizing your recovery. So with that, I'm going to end, and I'm going to introduce Ken, who's going to be moderating the panel. Now, Ken started out as a undergraduate in physics at MIT, and Ken had a roommate who was a geologist. And Ken was always jealous that his roommate could see the stuff that he was working on, as opposed to physics. It's all very kind of ethereal. And that was what won Ken over to this industry. Ken is now the Vice President of Geology and Reservoir Engineering. Close enough. At ConocoPhillips, and he'll be our moderator tonight. Thank you.